Hello, Assalamualaikum and good afternoon. Okay, in this video, we are going to continue our study in chapter 3 of transmission line parameters. This time, we are going to play with the capacitance. We have finished the inductance, we play with the line inductance, the transposition, the double circuit, and single circuit, single phase, two phase. Right now, go next for the capacitance, okay? So without further ado, let's go directly to the contents itself. So transmission lines, conductors exhibit capacitance also, not only inductance, but also another important parameter is capacitance. Capacitance also exists in this transmission line. Okay, with respect to each other due to the potential difference between them. As soon as the potential difference between two conductors, between two electrodes or two plates, terminals, there must be a capacitance. The capacitance is there, exists by nature. Okay. So the amount of capacitance for this case of transmission line between phase conductors is a function of conductor size. Okay, conductor size we have learned already. Conductor size means how big is the size of the cable. So when we say how big is it, the size means there's R there. R is the radius. So the radius, since it totally depends on the radius of the conductors. Okay, that's one thing. The other thing is spacing. Spacing when we have, for example, we have two phase conductors, for example here, then we have two phase conductors here. Okay, so there's difference. There's the distance between this. So this is D. This is what we call also spacing. Okay, spacing. And also the height above ground. Okay. So very simple equation that you have learned already in your first year studies. So C equal to Q over V. Okay. Logically, if we have two electrodes or two plates, okay, with this one is the plus and this one is the minus, okay, and we assume that we have the one charge here. The charge is moved towards this two electrodes, so it creates the potential difference. So this potential difference is the V. So this is the Q. So that's why the capacitance is the total charge, the Q, over the voltage difference, potential difference between these two plates. Then that's why the equation C equal to Q over V. Okay. And then what about the line capacitance? Okay. Let's consider we have the very long round conductor with radius R. Same cases with the inductance before, in the same figure, but this time we play with the charge. When you're saying about capacitance, there must be a charge. Okay. So this is the phase conductor. So this is a phase conductor with the round conductor. So originally the radius for this conductor is R, okay, and then it's carrying a charge of Q. So this phase conductor is carrying a Q charge, Q coulombs of charge, with the radius of R. Okay, so we assume as same like before inductance, we assume this one basically standard is 1 meter lah. We just assume that. Okay, at the first place. Right. So from here, what can we get? We can get the electrical flux density. Okay, electrical flux density. Electrical flux density at a cylinder of radius x is given by. Okay, here the electrical flux density here is defined as D. Okay, where the electrical flux density of D is the charge over the area of the conductor. Okay, the area of the conductor is the 2 pi r. Okay, it's 2 pi r. Okay, so got the circle one, of course, the circle one is 2 pi. And then for this case, we don't restrict to the radius of r, but we assume there's between this x. As if you check from here, there's x here. X is the any distance from the middle of the conductor, from the center of the conductor until x distance. Okay, so that's x is the distance here. So 2 pi x is the area of the conductor, of the area of the electrical flux density that we are talking about. Okay, so there is it. Okay, then from the electrical flux density, which is D, we can simply derive the electrical field intensity, or E. So the E is very simple, straightforward. So we just divide it with the epsilon 0, or stands for the permittivity of free space, is epsilon 0, and the value is fixed already. You cannot change it by your own will. It's fixed already. 8.85 multiplied with 10 to minus 12 farad over meter. So when we simplify it, then we get the Q over 2 pi epsilon 0 x with the additional epsilon 0 only. Okay. Then from there, so the potential difference. So the potential difference is equal actually the V, the potential difference, the V itself. So between cylinders from position D1 to D2 is defined as, if I check it back, okay, so I forgot to say it. So the position D1 is here and D2 is somewhere around here. Just the difference, the potential difference between the state of D1 and D2, okay? Between the D1 and the D2, okay? So that how to do that, okay, how to do that is how to do that, basically the E, okay, the V, okay, the V is the integration of the electrical field intensity from D1 to D2. It means that we integrate the value of this E, the function of this E, from D1 to D2. So because the X, so E dx. Then from here, we can get D1, D2, D1. So we get Q 2 pi epsilon 0 multiplied with 1 over x dx. So this is the function that we are going to integrate it. So this basically will become Q 2 pi epsilon 0, and it will become ln x, where it's from D2 to D1. Then you simply so this is the Q. Sorry for my bad handwriting. Okay, so 2 pi epsilon 0. So we get the ln D1 minus D2 minus D1. So basically you simplify it, then you get Q 2 pi epsilon 0 ln D2 over D1. Okay, 2 over 2. So then we get the potential difference. Okay, next for the single phase lines. Okay, so let's consider we have two long solid rod conductors. So we have first conductor here with the Q1, the charge of Q1, and we have the second conductor here with the Q2, and both conductors have the same radius of R. Okay, as usual, we consider it for the 1 meter length of these phase conductors. Okay, so what should we do? Because we are going to determine the capacitance. So first of all, from here, what we can do, with the difference of D between these two phase conductors, we can simply derive the potential difference. For this case, is from V1 to V2. I mean, from the point 1 to point 2. So this is the V1 to Q1. Okay, so simple. So we Q1, and we get 2 pi epsilon 0. It's fixed already. Ln, okay, with the shortest distance here is R. Okay, shortest distance is R. So the spacing between these two fingers is D, not D2, D, and the small one is R, because the shortest and the longest distance. Okay, same goes for the case of the second phase conductors. So this time is V21 and V21 with the Q2. Okay, then we have the Q2 2 phi epsilon 0, and since the distance also D and the radius R is almost the same with D of R. Okay, in for this case, so we want to do the superposition theorem. Okay, so that's why we need to make it same with the V12 also for this case. So if we try to do the V12, so with V12 for the case of Q2, okay, then we are going to get it's equal to the minus V21 Q2. Okay, so means that V12 Q2 is the Q2 minus Q2 25 epsilon 0 ln D over R. But we still have the minus, so minus we put it to the ln part to become with power of minus 1, so it become Q2, okay, Q2 2 pi epsilon 0 ln, this time is R over D, okay, R over D, okay. Then we get the for the case of V12 Q2, okay. So if you like, if you want to do the total of the V12, because we're doing the superposition, so this position is V12 Q1 plus V12 Q2, okay. So we just add it up, so it's become Q1 and Q2, but here you can also Q2, okay, if we try to solve it, so Q1 2 pi epsilon 0, okay, 0 ln D over R plus Q2, okay, Q2 2 pi epsilon 0 ln R over D, okay, right? Okay, by assuming that Q2, okay, assuming that here Q2 is equal to this minus Q1 and equal to minus Q, okay, minus Q, then here finally we can get the V12 is equal to Q pi delta 0 ln D over R. So we get 2 times of Q. We get 2 times, because we change it, this one with the minus Q. So at the end, this one will change to the minus Q. So when it comes minus Q, this R over D will inverse. Then that's why we get 2 over 2. We are going to get, understand what I'm saying? Means that finally we are going to get Q 2 pi epsilon 0, okay, epsilon 0 ln D over R, because the Q2 now is changed to the minus, okay, minus Q1 with the ln R over D, but same cases it become like this, Q 2 pi epsilon 0 ln R over D with the power of minus 1. That's why it also inverse, then you get 2Q over 2 pi epsilon 0 ln dr, so you can cancel out the 2 1, then finally you get Q, only Q is remaining here, so Q over pi epsilon 0 multiplied with ln D over R. This is for the case of farad over meter. Okay. Okay. Soon after we get the B12, so we already get B12 here. So simply use the first equation that we have learned in this video, which is the capacitance. So here the C12 equal to Q over B12, where there will be cancellation of Q from the original V12 equation that we have determined. So finally, it will give us the equation of C12 equal to pi epsilon 0 over ln D over R farad over meter. So this is the equation of the capacitance for the single phase lines. Okay. Alright. So okay, the equation gives the line to line capacitance between the conductors. So we have determined V12, C12 like that. So for the purpose of transmission line, okay, for the purpose of transmission line modeling, we find it convenient to define a capacitance C between each conductor and a neutral line. Okay, the difference between before. So for the case of transmission lines only, we are going to redefine the capacitance of C between the conductor and the neutral line. So it's S is better. Original that we have determined the C12 that we get just now. So this is the C12 that we just get just now. Sorry, it's the K ln D over R para better. Okay, syndrome. So this time there will be another definition of the capacitance, redefinition of the capacitance, because we consider phase conductors and also the neutral line here. Okay, so the different on this one. Okay, what is difference? The voltage to neutral is half of V12. Okay, voltage to neutral is half of V12. So voltage to neutral is half V12, means that V12 over 2, and from here is the V12 over 2. So if we add up the same value, we get V12. So that's why the capacitance to neutral is C equal to C12, because the voltage is already half. So it's very simple, because here C because original equation is C Q over V. V now become half. That's why we get 2C. And for this case, we get 2C. So mean that C1, the new C is equal to C12. So that's why we get another equation with only two different compared to the previous slide. Okay, so this is the equation. So this final equation for the capacitance of the single phase line that includes two phase conductors is C equal to 50 over ln D over R. So where D is the distance, okay, distance between phases, and the R is the radius of phase conductor. Okay, all right. Okay, let's do some exercises. So for me, there's no understanding without the exercise. Okay, that's my principle. Okay. Let's read the question. So N 132 kV and 50 Hz single phase 2-wire transmission line. Okay, they mentioned you already. The keywords here, single phase and 2-wire transmission line. So I mean we have two conductors. We're going to have two conductors. Okay. Then consists of aluminum conductors with diameter of 50 millimeters. Okay, diameter of 50 millimeter means diameter. Okay, so we get the clue. The first clue is diameter is 50 millimeters, which is equal to 0.05 meters. But once we get the diameter, it's very extremely simple to get the radius. It's the half of the diameter, so D over 2. Then you get the 0.025 meter is the radius R. Okay. Next, the two conductors are spaced 1.8 meter apart. So here, right here, so the D is 1.8 meters. Okay, very simple. Okay. Then the transmission line is 25 kilometers long. Okay. The cable that we have is 25 kilometers long. I don't know, maybe from here to Uday, maybe. I just guess. And then the temperature of the conductors is 20 degrees C. Apparently, this one is no need to concern. Okay, just ignore it. Also, because the question asking you calculate capacitance per kilometer. Capacitance again. So capacitance, we don't need this kind of value. We don't want to calculate the reactance, capacitive reactance, the reactance of capacitance. Okay. So this one no need to consider. Just erase it. So here the two clues here we get already, very straightforward. Then we get the D distance between both conductors is 1.8 meters, and then we get the radius with the 0.025 meter. So the first question asking you capacitance per kilometer means per kilometer how much is capacitance. Okay. The equation that I taught you in the last slide, the previous slide is in the farad over meter. Here, the farad over meter. But for the case of because they're asking you per kilometer basically it become over kilometer, and the farad is not farad, it's microfarad. So you can turn to page, there's notes in Word versions, chapter 3, okay, chapter 3 in kalam, chapter 3, kalam, chapter 3, line capacitance, sorry, my word very bad handwriting, page 4 of 19, okay, page 4 of 19 is in the green color, okay, green color, very detailed, I give you the reference, okay, very straightforward. C equal to 0.0556 over ln D over R in microfarad per kilometer. Okay, so you just put the value here, 0.0556 ln the D is the 1.8, and the R transmission, the radius is 0.025. Okay, 0.025. Oh, I don't have the answer here, and so need to bring my calculator. Sorry. Okay, let's calculate together, brother. Okay. Wait. Okay, 0.0556 0.0556 divide with ln, then itself is the 1.8 and the 0.025. Okay. Alright. So 0.025. Then from my answer, so I get 0.013 microfarad over kilometers. So this is what I get. You can check by yourself. Okay, you can check by yourself. Just simply put in the equation. Okay. Then we get the first. We done the first question. So second question asking you about the capacitance of this measuring line. What is this? This looks no different. No, it's different because we have 35 kilometer long. Very super easy. So we just multiply with the 0.013 multiply with 25 because per kilometer we get 0.013. So per 25 kilometers, that's simply 0.013 multiplied with 25. Then you get the capacitance of 0.325 microfarad. Okay, that's for 35 kilometers. Okay, all right.